Hi, and welcome to my video presentation on the life cycle of a star, as you can see in the text that I will hopefully be managing to edit on later. Let's get crack-a-lacking. Crack-a-lacking? Never mind. Okay, so I feel like the first question to ask is, quite naturally, how is a star formed? Well, basically, there's this thing called a stellar nebula, which is basically a big ball of gas and dust and hydrogen that over millions of years is pulled together by gravity. Then the particles in it start to move faster and faster and faster and reach millions of degrees. Whoop! And I don't know what that sound effect was, please ignore it. And they form a protostar. And this happens when a hydrogen, I don't actually have a hydrogen, so I'm just going to write one. Nuclei fuses to make helium, and this is meant to be helium, but you know. Yeah. The star then enters a long, stable period where the outward pressure of fusion is counterbalanced by the force of gravity. This is now called a main sequence star, and it stays in this state for like 10 million to 10 billion years. That's a long time. Like, humans only live to 100. Wow. Anyway. So then what happens next depends on the size of the star. And it can either be a small star, like our sun. Yes, our sun, despite being way bigger than us, is a small star. Just think about that. Think about we're tiny humans on a tiny planet revolving around quite a small star, and have a mini existential crisis. Anyway, and a big star, and these take two different routes because of the way they meet up. I will explain more later in the video. Okay, so we'll talk about a small star first, like our sun. So eventually, like all things, the hydrogen that's making the fusion happen here will run out, and when that happens, the star will collapse in on itself. And when it my sound effects are amazing. It will increase the heat. The heat will increase. Oh, I don't even know what I'm saying anymore. Anyway, it will become so hot that it can the helium can fuse together to make other elements, all the way up to iron. To form elements heavier than iron, however, it would require an input of energy, as seen in this lovely diagram, which it doesn't have. The star then expands. Bam! Oh, let's pretend that was much less clumsy than what it actually was. The star then expands to become a red giant. When our sun does this, it will expand so big that it will engulf all three inner planets. So that's fun. We're doomed, but you know, climate change or politics might get us there first. So who knows? So next, fusion of helium in it will suddenly stop because it's run out yet again, and it will suddenly go inwards to form a white dwarf. And because no more fusion is occurring, it really cools down so much until it becomes, there we go, a black dwarf, which is as cold as the surroundingness. Yes, that's a word now. But this is only after like billions years of cooling. It stops releasing heat. Okay, so what about big stars? Because this is basically it for a small star. It's kind of sad, but you know, circle of life and all that. So basically, a big star, it will also run out, but it will run out much more quickly than a small star will. So it has a much shorter main sequence life than a relatively small star. These stars then expand to become super red giants, and I don't have a label / drawing for that because I don't. I forgot to make one. Don't try to shoot me. But you know, we'll just have a worm on a string. So that's a super red giant, if you can stretch far enough in your imagination to think of that. And this is now full of all of the elements up to iron. Again, eventually fusion will stop, and again, eventually it will collapse. When it does collapse, it will create a huge explosion of energy, like well, not quite like that, but you know, like that, which will create a supernova, and it creates so much heat and light in this outpour of energy, and it can carry on for many, many weeks. There is an extremely high temperature and pressure, as you can see on this label, in the supernova, which allows it to create all of the elements, and then it distributes them out throughout the universe. And, you know, that's how you get elements. And I think that's pretty nice, because it essentially means that we're all made of stardust, and that I like that idea. Maybe you don't, but I do. Now, two different things can happen after that. Either a neutron star or a black hole is formed. And we all know about black holes. We can't directly observe them, as you can see in this little label. Oh no, you can't see, it's all the way over here. There we go. As you can see in this little label, we can't observe them, but we can see the effects of them on other things such as stars. And they have a huge, strong, really like immense gravity that like sucks everything in, hence why we can't see them, and even light. Yes. Blah, blah, blah. A neutron star, as you probably may guess, is made up of densely packed neutrons. What a shocker. And this is when, under immense pressure, electrons, I know, lovely little e, are forced to merge with protons. And then the black hole is formed after the neutron star if this neutron star, if the mass of the neutron star is sufficiently high to cause even further gravitational collapse. So yeah, that's kind of, you know, my explanation of stars in a nutshell, and worms on strings apparently. Thank you for bearing with me and listening. And just, yeah, I hope you learned something. And future Karis, I apologise for babbling on so much. Sorry is all I have to say.